हेलो एवरीवन, वंस अगेन वेलकम बैक टू आवर चैनल बीटदनीट। और आज मैं करने वाली हूँ क्लास 12th केमिकल काइनेटिक्स चैप्टर। इसका पार्ट 1 ऑलरेडी अपलोड है, इसका लिंक डिस्क्रिप्शन में मैंने दे दिया है, तो जिनके पास में नहीं है वो वहां से जाकर के देख सकते हैं। बाकी सेकंड पार्ट में आज आप लोगों के साथ में यहाँ रिकॉर्ड कर रही हूँ। बच्चों, दिस इज ओनली एंड ओनली एन ऑडियो बुक, नॉट द एक्सप्लेनेटरी वन, सो बी स्पेसिफिक व्हेन यू आर लिसनिंग इट। सो चलिए स्टार्ट करते हैं। इसको अगर आपको लगता है कि आपकी इससे हेल्प हो रही हो तो इसे लाइक जरूर कीजिएगा, शेयर कीजिएगा, और अगर चैनल पर नए हो तो सब्सक्राइब भी कीजिएगा। अपने दोस्तों को जरूर बताइएगा ताकि उनको भी इसका बेनिफिट मिल सके। चलिए टाइम वेस्ट नहीं करते हैं और इसको शुरू करते हैं। 4.3.2 First order reactions. In this class of reactions, the rate of the reaction is proportional to the first power of the concentration of the reactant R. For example, R gives P. Rate is equals to minus dr upon dt is equals to kr, or dr upon r is equals to minus k dt. Integrating this equation, we get ln r is equals to minus kt plus I. Again, I is the constant of integration and its value can be determined easily. When t is equals to 0, r is equals to r naught, where r naught is the initial concentration of the reactant. Therefore, equation 4.8 can be written as ln r naught is equals to minus k into 0 plus I, and ln r naught is equals to, or r0 is equals to I. Substituting the value of I in equation 4.8, we will get ln r is equals to minus kt plus ln r naught. Rearranging this equation, ln r upon r naught is equals to minus kt, or k is equals to 1 upon t ln r naught upon r. At time t1 from equation 4.8, ln r1 is equals to minus kt1 plus ln r naught. At time t2, ln r2 is equals to minus kt2 plus ln r naught, where r1 and r2 are the concentration of the reactants at the time t1 and t2 respectively. Subtracting 4.12 from 4.11, then we will get ln r1 minus ln r2 is equals to minus kt1 minus kt2. ln r1 upon r2 is equals to kt2 minus t1. So k is equals to 1 upon t2 minus t1 ln r1 upon r2. Equation 4.9 can also be written as ln r upon r naught is equals to minus kt. Taking anti-log of both sides, r is equals to r naught e to the power minus kt. Now comparing equation 4.9 with y is equals to mx plus c, if we plot ln r against t, we get a straight line with slope is equals to minus k and intercept equal to ln r naught. The first order rate equation 4.10 can also be written in the form of k is equals to 2.303 log r naught upon r. So log r naught upon r is equals to kt upon 2.303. If we plot a graph between log r naught upon r versus t, the slope is equals to k upon 2.303. Hydrogenation of ethane is an example of first order reaction. C2H4 plus H2 gives out C2H6. Rate is equals to K C2H4. All natural and artificial radioactive decay of unstable nuclei takes place by first order kinetics. See the figure 4.4 and 4.5. 22688 radian gives out 24He plus 86222 Rn. Rate is equals to Kra. Decomposition of N2O5 and N2O are some more example of first order reactions. Let us consider a typical first order gas phase reaction. A gives out B plus C. Let Pi the initial pressure of A and Pt the total pressure at time t. Integrated rate equation for such a reaction can be derived as total pressure is Pt is equals to Pa plus Pb plus Pc, that is the pressure units. Pa, Pb and Pc are the partial pressure of A, B and C respectively. If X be the decrease in pressure of A at time t and 1 mole each of B and C is being formed, the increase in pressure of B and C will also be X each. So here you can see at time t is equals to 0 and at time t. And here you can see the all calculation. And the final we are getting the KL is equals to 2.303 upon T log Pi upon 2 Pi minus Pt. 4.3.3 Half-life of a reaction. The half-life of a reaction is the time in which the concentration of a reactant is reduced to one half of its initial concentration. It is represented as T half. For a zero-order reaction, rate constant is given by equation 4.7. K is equals to R naught minus R upon T. So T is equals to T half. So R is equals to 1 by 2 R naught. The rate constant at T and a half becomes the final value of T and a half we will get here R naught upon 2K. It is clear that T and a half for a zero order reaction is directly proportional to the initial concentration of the reactants and inversely proportional to the rate constant. Now for the first order reaction, the value of K is equals to 2.303 upon T log R naught upon R, and the T half and R is equals to R naught upon 2. So here the final value we will get of T and half is equals to 2.693 upon K. The calculation you can see here. It can be seen that for a first order reaction, half period is constant, that is, it is independent of initial concentration of the reacting species. The half-life of a first order equation is readily calculated from the rate constant and vice versa. For zero order reaction, T and half is proportional to R naught. For first order reaction, T and half is independent of R naught. Now we are having a table 4.4 summarizes the mathematical features of integrated laws of zero and first order reaction. This is the table 4.4 integrated rate laws for the reaction of zero and first order. The order of a reaction is sometimes altered by condition. There are many reactions which obey first order rate law, although they are higher order reactions. Consider the hydrolysis of ethyl acetate, which is chemical reaction between ethyl acetate and water. In reality, it is a second order reaction and concentration of both ethyl acetate and water affect the rate of reaction. But water is taken in large excess for hydrolysis. Therefore, concentration of water is not altered much during the reaction. Thus, the rate of reaction is affected by concentration of ethyl acetate only. For example, during the hydrolysis of 0.01 mole of ethyl acetate with 10 mole of water, amounts of the reactants and products at the beginning T is equals to 0 and completion of the reaction are given as under CH3COO C2H5 plus H2O gives out CH3COOH plus C2H5. Here you can see the values at T is equals to 0 and at time T. The concentration of water does not get altered much during the course of the reaction, so this reaction behaves as first order reaction. Such reactions are also called pseudo first order reaction. Inversion of cane sugar is another pseudo first order reaction, that is C12H22O11 plus H2O gives out C6H12O6 plus C6H12O6, that is glucose and fructose. Here the rate is equals to K C12H22O11. 4.4 Temperature dependence of the rate of reaction. Most of the chemical reactions are accelerated by increase in temperature. For example, in decomposition of N2O5, the time taken for half of the original amount of material to decompose is 12 minutes at 50 degrees Celsius, 5 hours at 25 degrees Celsius, and 10 days at 0 degrees Celsius. You also know that in a mixture of potassium permanganate and oxalic acid, potassium permanganate gets decolorized faster at a higher temperature than at a lower temperature. It has been found that for a chemical reaction with rise in temperature by 10 degrees, the rate constant is nearly doubled. The temperature dependence of the rate of a chemical reaction can be accurately explained by Arrhenius equation. It was first proposed by Dutch chemist J.H. van 't Hoff, but Swedish chemist Arrhenius provided its physical justification and interpretation. K is equals to A e to the power minus E upon RT, where A is the Arrhenius factor or the frequency factor. It is also called pre-exponential factor. It is a constant specific to a particular reaction. R is a gas constant and EA is the activation energy measured in joules per mole. It can be understood clearly using the following simple reaction, that is H2 plus I2 gives out 2HI. According to Arrhenius, this reaction can take place only when a molecule of hydrogen and molecule of iodine collide to form an unstable intermediate. It exists for a very short time and then breaks up to form two molecules of hydrogen iodide. The energy required to form this intermediate called activated complex is known as activation energy. That is obtained by plotting potential energy versus reaction coordinate. Reaction coordinate represents the profile of energy change when reactants change into products. Some energy is released when the complex decomposes to form products, so the final enthalpy of the reaction depends upon the nature of reactants and products. All the molecules in the reacting species do not have the same kinetic energy. Since it is difficult to predict the behavior of any one molecule with precision, that is, Ludwig Boltzmann and James Clerk Maxwell used statistics to predict the behavior of large number of molecules. According to them, the distribution of kinetic energy may be described by plotting the fraction of molecules Ne upon Nt with a given kinetic energy versus kinetic energy. Here, Ne is the number of molecules with energy E and Nt is the total number of molecules. The peak of the curve corresponds to the most probable kinetic energy, that is kinetic energy of maximum fraction of molecules. There are decreasing number of molecules with energies higher or lower than this value. When the temperature is raised, the maximum of the curve moves to the higher energy value and the curve broadens out, that is, spreads to the right such that there is a greater proportion of molecules with much higher energies. The area under the curve must be constant since total probability must be 1 at all times. We can mark the position of EA on Maxwell-Boltzmann distribution curve. Here you can see the figure 4.9. Distribution curve showing temperature dependence of rate of a reaction. Increasing the temperature of the substance increases the fraction of molecules which collide with energies greater than EA. It is clear from the diagram that in the curve at T plus 10, the area showing the fraction of molecule having energy equal to or greater than activation energy gets doubled, leading to doubling the rate of reaction. In the Arrhenius equation 4.18, the factor e to the power minus EA upon RT corresponds to the fraction of molecules that have kinetic energy greater than EA. Taking natural logarithm of both sides of equation, ln k is equals to minus EA upon RT plus ln A. The plot of ln k versus 1 upon t gives a straight line according to the equation as shown in figure 4.10. Thus, it has been found from Arrhenius equation that increasing temperature, the decreasing the activation energy will result in an increase in the rate of reaction and an exponential increase in the rate constant. In figure 4.10, here is the figure 4.10, a plot between ln k and 1 upon t. Slope is equals to minus EA upon R and intercept ln A. So we can calculate EA and A using these values. At temperature T1, equation 4.19. ln K1 is equals to minus EA upon RT1 and plus ln A. At temperature T2, equation 4.19 is ln K2 is equals to minus EA upon RT2 plus ln A. Since A is constant for a given reaction, K1 and K2 are the values of rate constant at temperatures T1 and T2 respectively. Subtracting equation 4.20 from 4.21, we obtain ln K2 minus ln K1 is equals to EA upon RT1 minus EA upon RT2. And finally, we are getting here the log K2 upon K1 is equals to EA upon 2.303 R in bracket T2 minus T1 upon T1 of T2. 4.41 Effect of catalyst. A catalyst is a substance which increases the rate of reaction without itself undergoing any permanent chemical change. For example, MnO2 catalyzes the following reaction so as to increase its rate considerably. 2KClO3 gives out 2KCl plus 3O2 in the presence of MnO2. The word catalyst should not be used when the added substance reduces the rate of reaction. The substance is then called inhibitor. The action of the catalyst can be explained by intermediate complex theory. According to this theory, a catalyst participates in a chemical reaction by forming temporary bonds with the reactants, resulting in an intermediate complex. This has a transitory existence and decomposes to yield products and the catalyst. It is believed that the catalyst provides an alternate pathway or reaction mechanism by reducing the activation energy between reactants and products and hence lowering the potential energy barrier as shown in figure 4.11. Here you can see figure 4.11, effect of catalyst on activation energy. It is clear from Arrhenius equation that lower the value of activation energy, faster will be the rate of reaction. A small amount of the catalyst can catalyze a large amount of reactants. A catalyst does not alter Gibbs energy, delta G of a reaction. It catalyzes the spontaneous reaction but does not catalyze non-spontaneous reactions. It is also found that a catalyst does not change the equilibrium constant of a reaction, rather it helps in attaining the equilibrium faster. That is, it catalyzes the forward as well as the backward reaction to the same extent so that equilibrium state remains same but is reached earlier. 4.5 Collision theory of chemical reactions. Though Arrhenius equation is applicable under a wide range of circumstances, collision theory, which was developed by Max Strauss and William Lewis in 1916-18, provides a greater insight into the energetic and mechanistic aspects of reaction. It is based on kinetic theory of gases. According to this theory, the reactant molecules are assumed to be hard sphere and reaction is postulated to occur when molecules collide with each other. The number of collisions per second per unit volume of the reaction mixture is known as collision frequency. Another factor which affects the rate of chemical reaction is activation energy, as we have already studied for a biomolecular elementary reaction. A plus B gives out product. Rate of reaction can be expressed as rate is equals to ZAB e to the power minus EA upon RT, where ZAB represent the collision frequency of the reactants, A and B, and e to the power minus EA upon RT represent the fraction of molecules with energies equal to or greater than EA. Comparing 4.23 with Arrhenius equation, we can say that A is related to collision frequency. Equation 4.23 predicts the value of rate constants fairly accurately for the reactions that involve atomic species or simple molecule, but for complex molecules, significant deviation are observed. The reason could be that all collisions do not lead to the formation of products. The collision in which molecules collide with sufficient kinetic energy, called threshold energy, and proper orientation, so as to facilitate breaking of bonds between reacting species and formation of new bonds to form products are called as effective collisions. For example, formation of methanol from bromomethane depends upon the orientation of reactant molecules, as shown in figure 4.12. The proper orientation of reactant molecules lead to bond formation, whereas improper orientation makes them simply bounce back and no product are formed. To account for effective collision, another factor P called the probability or steric factor is introduced. It takes into account that the fact that in a collision molecules must be properly orientated, that is, rate is equals to PZAB e to the power minus E upon RT. Thus, in collision theory, activation energy and proper orientation of the molecules together determine the criteria for an effective collision and hence the rate of chemical reaction. Collision theory also has certain drawbacks, as it considers atoms, molecules to be hard spheres and ignore their structural aspects. You will study detail about this theory and more on other theories in your higher classes. Threshold energy is equals to activation energy plus energy possessed by the reacting species. Summary. Chemical kinetics is the study of chemical reaction with respect to reaction rates, effect of various variables, rearrangements of atoms, and formation of intermediates. The rate of reaction is concerned with decrease in concentration of reactants or increase in the concentration of products per unit time. It can be expressed as instantaneous rate at a particular instant of time and average rate over a large interval of time. A number of factors such as temperature, concentration of reactants, catalyst, effect of rate of reaction. Mathematical representation of rate of reaction is given by rate law. It has to be determined experimentally and cannot be predicted. Order of a reaction with respect to a reactant is the power of its concentration, which appears in the rate law equation. The order of a reaction is the sum of all such powers of concentration of terms for different reactants. Rate constant is the proportionality factor in the rate law. Rate constant and order of a reaction can be determined from the rate law or its integrated rate equation. Molecularity is defined only for an elementary reaction. Its values are limited from 1 to 3, whereas order can be 0, 1, 2, 3 or even a fraction. Molecularity and order of an elementary reaction are same. Temperature dependence of rate constant is described by Arrhenius equation. EA corresponds to the activation energy and is given by the energy difference between activated complex and the reactant molecules, and A is the Arrhenius factor or pre-exponential factor, correspond to the collision frequency. The equation clearly shows that increase of temperature or lowering of EA will lead to an increase in the rate of reaction and presence of catalyst lowers the activation energy by providing an alternate path of the reaction. According to collision theory, another factor P called steric factor, which refers to the orientation of molecules which collide, is important and contributes to effective collisions, thus modifying the Arrhenius equation to K is equals to PZAB E to the power minus EA upon RT. चैप्टर डन। थैंक यू सो मच एवरीवन। सो बच्चों, आप लोगों को ये वीडियो कैसा लगा मुझे कमेंट सेक्शन में जरूर बताइएगा। नेक्स्ट आपको कौन सा चैप्टर चाहिए ये भी आप मुझे कमेंट सेक्शन में बता सकते हैं। जल्दी हमारा 11th और 12th के केमिस्ट्री के सारे चैप्टर्स कंप्लीट होने वाले हैं। तो अगर ये वीडियोस आपकी हेल्प करते हैं, ये ऑडियो बुक्स आपकी हेल्प करती हैं, तो इसके लिए आप इसको लाइक जरूर कीजिएगा और अपने दोस्तों से शेयर करिएगा। और अगर आप हमारे चैनल पर नए हैं तो इसे सब्सक्राइब कीजिएगा। टेक केयर एवरीवन, सी यू सून इन माय नेक्स्ट वीडियो। टिल देन जस्ट स्टे ट्यून्ड विद मी। बाय बाय।